Hello, and welcome to our example of using the Fourier transform to solve a very familiar ODE, which is f double prime minus f equals g of x. So here g is given to us, and we want to find f. So let's begin by working backwards. We'll take the Fourier transform of both sides of this ODE and see what it tells us about f. That is, we assume we have a solution, and we want to use the transform to find a formula for that solution. So we have g hat of k is f double prime minus f whole thing hat of k. Linearity of the Fourier transform says that is f double prime hat of k minus f hat of k. And then we use our favorite Fourier property for the derivative. This is ik f prime hat of k minus f hat of k. This is ik squared f hat of k minus f hat of k. Every time you see a prime, that gives you an ik factor. This is minus k squared f hat of k minus f hat of k. That is minus 1 plus k squared f hat of k. So now we can solve for f hat of k. If g hat of k equals minus 1 plus k squared f hat of k, then f hat of k is minus g hat of k divided by 1 plus k squared. 1 plus k squared, we know, is positive as long as k is real, so I have no problems with the division here. Now, what do I need for this to work? Well, I would need f prime, f double prime, and g all to be L1 because I want all of these Fourier transforms to be defined. And so if I have f hat of k equals minus g hat of k over 1 plus k squared, then I should be able to invert the transform and get f of x equals inverse Fourier transform of minus g hat of k over 1 plus k squared on x. So here I'm using a convention that I'll often use in these notes. If I have a formula that depends on k, I'll just stick the whole formula inside the square brackets for the inverse Fourier transform. Now, is this actually a solution? Because remember, I'm working backwards. I started out assuming that I was able to solve this differential equation, and that told me that the solution had to have the form f of x is inverse Fourier transform of this stuff in the square brackets at x. So is this formula actually differentiable, and does the derivative fit into the differential equation nicely? Well, let's think a little. If I have my function g in L1 of r, which is what I need for g hat to be defined, or what makes g hat defined easily enough, then I know that g hat is continuous. That's a Fourier fact from last week. And I also have a sort of Sobolev estimate. The maximum of the modulus of g hat of k for all k in the reals is less than or equal to the L1 norm of g. So all the Fourier transform values, g hat of k, are bounded by L1 norm of g. So let's look at the mapping that's inside those square brackets. K is mapped to minus g hat of k over 1 plus k squared. This is a continuous mapping, because clearly 1 plus k squared is continuous and g hat is continuous. And it's bounded above by L1 norm of g divided by 1 plus k squared. So this is a locally integrable map because it's continuous, and it's bounded by this thing, L1 norm of g over 1 plus k squared, and we know that map is in L1 of r. So the comparison test tells me that k goes to minus g hat of k over 1 plus k squared is an L1 map. And what does that mean? First of all, that this inverse Fourier transform is actually defined, because minus g hat of k over 1 plus k squared is an L1, so its Fourier transform, its inverse Fourier transform are both defined. And of course, I could write this inverse Fourier transform on the stuff in square brackets as the Fourier transform on the stuff in square brackets evaluated at minus x. So now, are these transforms differentiable? We know they're well defined, provided that g is an L1, but are they differentiable? Well, here we need another Fourier fact from last week. Say you have a function h in L1, and the integral from minus infinity to infinity of the modulus of x times h of x converges. Not just the integral of modulus of h, but integral of modulus x times h of x. Then h hat is differentiable with respect to the Fourier variable k, and the k derivative on h hat at k is minus I times the Fourier transform of x, h of x at k. So this Fourier transform on the right, Fourier transform of x, h of x, that's defined because the integral of modulus x, h of x converges. And then you have this important factor of minus I on the outside. And remember, if you read the notes and the proof of that, we saw that it comes from differentiating under the integral. You pass the k derivative under the integral, and a factor of minus ix pops out from the chain rule. Don't forget this factor of minus I in front of the f. I did when writing the slides for this video, and it took me about an hour to figure out what I was doing wrong. So this weird factor of minus I is really important in the derivative. So that's one derivative of the Fourier transform, but we have a second order differential equation here. So if we want to do two derivatives, we would want the integral from minus infinity to infinity of modulus of x squared h of x to converge. And then h hat is twice differentiable, and its second derivative will be minus Fourier transform on x squared h of x at k. So if I do the first derivative, I get a factor of minus I. If I do the second derivative, I get a factor of minus I quantity squared, which gives me just the plain old minus in front of f here. So with these Fourier facts, I can differentiate my given function f is inverse Fourier transform of minus g hat of k over 1 plus k squared. Or I could just switch to the regular Fourier transform evaluated at minus x. So is this function twice differentiable? Well, we would need the following thing. The integral from minus infinity to infinity of k squared over 1 plus k squared times modulus of g hat to converge. And does that happen? Well, that happens because I know the integral from minus infinity to infinity of modulus of g hat converges. Since this factor k squared over 1 plus k squared is always between 0 and 1. So I should say this happens if g hat is improperly integrable. Remember, we assumed at the start that g was in L1, and now if we assume that g hat is also in L1, then we get this good convergence of the integral k squared over 1 plus k squared g hat modulus. And so we can solve the ODE. Indeed, we check this with f of x equal to the Fourier transform of minus g hat of k over 1 plus k squared at minus x. We differentiate it one time with respect to x to get minus I times the Fourier transform of minus k g hat of k over 1 plus k squared at minus x. And that turns out to be I times the Fourier transform of k g hat of k over 1 plus k squared at minus x. Differentiate it again to get f double prime equals minus I squared, Fourier transform k squared times g hat of k over 1 plus k squared at minus x, which just becomes Fourier transform of k squared, g hat of k over 1 plus k squared at minus x. So here I'm using all the properties of the Fourier transform's derivative from the previous slide. And then I just subtract f double prime of x minus f of x is Fourier transform at k squared g hat of k over 1 plus k squared at minus x plus Fourier transform g hat of k over 1 plus k squared at minus x. And that's Fourier transform 1 plus k squared times g hat of k over 1 plus k squared at minus x. Fourier transform g hat of k at minus x. And then I do the switcheroo to get back to the inverse Fourier transform. This is inverse Fourier transform g hat of k at x. And hopefully this is g of x. So to get that to work out, I really want g to be piecewise continuously differentiable, so I can use the inverse Fourier transform theorem. And I also want g to be continuous, so I don't have to deal with left and right hand limits. So here's really what I want G to do. I want this non-homogeneity, this right-hand side G from my original differential equation, to be in L1, and to be piecewise continuously differentiable, and to be continuous, and to have G hat in L1. So remember, I've said this a couple times this week already, if G is in L1, that means G hat is defined, but that does not guarantee you to have G hat in L1. If G is piecewise continuously differentiable, well, G could still be discontinuous at some places, so assuming that G is in both C1 piecewise and C of R is not redundant. This is asking a lot on G, isn't it? I want G to live in the intersection of three function spaces, and I want its Fourier transform to be nice. Why am I doing this to you? Why all this fuss, when for this very simple differential equation that we're studying, we could just have used variation of parameters as we learned back in the first 2 weeks of the course? Why should we kill ourselves with the Fourier transform here? So what is the point of all this? This is I've separated out as a separate example and discussion in the lecture notes. If we want to solve this differential equation, f double prime minus f equals g of x with the Fourier transform, we need to assume more about G than G just being continuous, which suffices for variation of parameters. This is because to use the Fourier transform, we need the derivatives f, f prime, and f double prime to all be in L1. It turns out that if you want f, f prime, and f double prime all in L1, you need some decay on f. You need the limit as x goes to plus or minus infinity of f to be the same as the limit as x goes to plus or minus infinity of f prime to be 0. And this is something that arose in our study just of the Fourier transform and derivatives in the first place last week. So if you have a function that's differentiable, and that function and its derivatives are in L1, then the function has to vanish at infinity. So what is this saying? Using the Fourier transform for this very simple, this toy differential equation, really means we're studying a boundary value problem. We have a derivative part, f double prime minus f equals g, and we have boundary conditions for f and f prime that their limits at plus or minus infinity are 0. So we don't just want f to solve a differential equation, we want f and f prime to satisfy 4 different limits at plus or minus infinity. And as we know from a few examples here and there in the course, boundary value problems take more work than initial value problems or plain old ODEs. Boundary value problems are a little harder to solve, and we will do this in much more detail in the coming weeks too. But hopefully you're asking yourselves, and me right now, why are we using the Fourier transform in the first place for this differential equation? You might think there's no need for the Fourier transform other than as a teaching tool to see how to play around with Fourier mechanics to solve something that we know how to solve. Why would somebody use the Fourier transform to solve a differential equation? Isn't it artificial that we're imposing these extra decay requirements on the function f? Maybe not. There are a variety of applications and problems that arise from physics or modeling something in the real world where you want your solution to decay in a nice way. Maybe the solution is the profile of a wave on a canal, as you might see if you open your window and look out at the canal that's probably nearby you. Waves often decay far away from some core. Maybe F is modeling the energy of some system that inherently is in L1 or L2 and has nice integrability properties. So there are a lot of problems where it's natural to use the Fourier transform, and even for a simple differential equation, to assume that the function has sufficient decay that all this Fourier stuff is defined. So for this simple problem, yes, it's a little strange to use the transform. For other problems, no, it's a natural and healthy thing to do. And third, we know how to solve this problem in the first place using variation of parameters. Does variation of parameters still work here? Do we get the same variation of parameters solution with the Fourier transform? So, a fundamental solution set for our homogeneous problem, f double prime minus f, is e to the x and e to the minus x. So we should be able to write our solution in the following form. F of x should be a constant c1 times e to the x, plus c2 times e to the minus x. then times this mess from variation of parameters and the Vronsky and the particular solution. So the extra terms in f, the particular solution, when we want to solve f double prime minus f equals g, we have this e to the x over 2, integral 0 to x, e to the minus c g of c, minus e to the minus x over 2, integral 0 to x, e to the c g of c. And if this feels strange to you, you should hit pause and work out variation of parameters right now, because that's definitely something you need to know, say, for your exam coming in a week or two. So I'm going to call this form of f star. Any solution to our original ODE has to be written in the form star for some choices of C1 and C2. Now the Fourier transform tells us that if we have f double prime minus f equals g, and we have all these extra good requirements on g, then the solution is f of x equals minus inverse Fourier transform g hat of k over 1 plus k squared at x. How on earth do you turn that formula for f into star? It turns out you can evaluate this inverse transform using convolution if you remember that the inverse transform of 1 over 1 plus k squared at x is root pi over 2 e to the minus absolute value of x. That is an example that we do in the notes. And if you do the convolution and you grind through a few calculations here and there and do the arithmetic right, it turns out that this inverse Fourier transform on f really reads f of x equals 1/2 times the integral from minus infinity to infinity of e to the minus absolute value of x minus c times g of c dc. So if you split this integral up in the right way using absolute value, and by right way I mean what I do in the notes, I won't subject you to that here, then f will have the form star from variation of parameters if you take your constant c1 to be minus 1/2 integral 0 to infinity e to the minus c g of c, and c2 to be minus 1/2 integral minus infinity to 0 e to the c g of c. So from this very elaborate Fourier setup, we recover what we expect from variation of parameters. The difference is that variation of parameters works as long as the non-homogeneity g is continuous. For the Fourier transform to produce a solution, we need a lot more on g and also g hat. On the other hand, with this Fourier transform solution, we know that our function f isn't just twice differentiable in a solution. We know it has special decay properties at plus or minus infinity, which could be important for an application.